Hello everybody and welcome to my talk. My name is Niels van Weide and I will tell you something about my paper called Constructing Higher Inductive Types as Groupoid Quotients. The setting of this paper is Homotopy type theory, and let me start by introducing Homotopy type theory. Homotopy type theory, abbreviated as HOTT, is a different foundations for mathematics and computer science. It is a variant of type theory, and thus we have both types and terms in this setting. The interesting aspect of HOTT is the treatment of equality. In type theory, equality is usually represented by propositional equality. That means if we have terms A and B of type A, we have a type A equals B, and terms of that type represents proof of equality. The type A equals B is called propositional equality. If we interpret types as sets, then propositional equality is interpreted as equality of sets. As such, there's at most one proof of equality. HOTT takes a different viewpoint toward equality. Equality in HOTT is treated as a proof-relevant relation, and as such, proofs of equality can be used in computations. For this reason, we also must view types differently. Instead of seeing them as sets, we interpret them as spaces. Let me be a bit more complete on that. In HOTT, a type is viewed as a space, or more precisely, you view a type as a simplicial set, a cubical set, or a topological space. A term is viewed as a point in a space, so a term of type A represents a point in the space A. Equality of terms is not viewed as two points being equal, but instead an equality between points x and y represents a path from x to y. Two paths are considered to be equal if we have a homotopy between them, and as a consequence, not every two proofs of equality are equal. While in general, types can have a rather complicated equality relation, we work in a simpler setting in this talk. We focus our attention to one truncated types. To define what those types are, we first talk about sets. A set is a type for which all proofs of equality are equal, and the reason why you call them set is because they behave similarly to sets in set theory. More precisely, a type is a set if every P and Q of type X equals Y is equal. A one-type is a type for which every X equals Y is a set. This means that there could be multiple proofs that X and Y are equal, but there's at most one proof that P and Q are equal if we have P and Q of type X equals Y. Such types are similar to groupoids. The point represents the objects in the groupoid, and the spaces X equals Y represent the morphisms in the groupoid. The main topic of this talk is higher inductive types, and we abbreviate that by HITs. Higher inductive types are an important feature in HOTT since they allow you to define types by specifying arities for the constructors for the points, paths, higher paths, and so on. For this reason, you can use them to define numerous interesting types. For example, you can use them to define spaces from topology. The circle, the torus, Eilenberg-MacLane spaces, all of them can be defined as a higher inductive type. Furthermore, you can use higher inductive types to define interesting examples from algebra, namely initial algebras and the free monoidal category. Furthermore, you can use higher inductive types to define the type of integers in such a way that you get a nicer induction principle. This is demonstrated by Altenkirch and Skokela, and if you want to know more about it, you can watch their talk in this conference. Let us illustrate higher inductive types by looking more closely at some examples. The first example we look at is the circle, and this type has two constructors. First of all, we have base, and this is just a point in the circle. It is the base point. Second, we have a path constructor loop, which is a path from base to base. It represents the loop of the circle. Another interesting example is the torus. This one again has a base point, which is just a point in the torus, and it has two path constructors, loop L and loop R, of type base equals base. Furthermore, we have a higher path constructor, surf. It is the surface of the torus. And here we use the notation bullet to denote path concatenation. The last example I will show you is the set truncation. Suppose we have a type A, then the set truncation of A is the smallest set such that we have an inclusion from A to that set. What is interesting about the set truncation is that the higher inductive type is recursive. Both X and Y and P and Q refer to the type being defined. The main goal of this talk is to reduce one-truncated higher inductive types to simpler principles. More specifically, we show how to construct one-truncated higher inductive types from a simple higher inductive type, namely the Groupoid Quotient. In this talk we will treat the following topics. We start by giving a signature for higher inductive types. After that we discuss the Groupoid Quotient, which is the main tool we use to construct higher inductive types. And we finish by formulating the Main Theorem and giving a sketch of the proof. We also highlight some interesting steps in the proof. In this talk we are interested in higher inductive types of the following shape. First of all, there's a point constructor. Second of all, there's a path constructor. Third of all, there's a homotopy constructor. And lastly, we have a constructor which says that the type is one-truncated. Note that P can depend on C and that S can depend on P. And note that all of these constructors can be recursive. Also, due to the constructor T, we can only eliminate these types into one types. The arity of the point constructor is specified by a polynomial functor P, and the type of codes for polynomials is defined inductively. We have codes for the identity polynomial, constant polynomial, sums, and products. Next, we look at the path constructor, and note that this one can make use of C. If you look at the type of the path constructor, you can see that it consists of several pieces of data. First of all, we have the type I. This specifies the labels of the path, so the names of each path. Second of all, we have Qj. This is a polynomial which represents the arguments of the equation. Lastly, we have Lj and Rj, which specify the left and the right hand side of the equation. A path endpoint represents a natural transformations between two polynomials which can make use of some constructor. P and Q represents the source and the target of the path endpoint, while A represents the arguments of the constructor it can use. The type of path endpoint is defined inductively, and it has various constructors, and we only highlight 3 of them, namely the identity, composition, and the constructor. The last part of the signature represents the homotopy constructor, and here we assume that C and P are already given. To specify S, we need to give a type J, which represents the names of all the homotopy constructors. For each J in J, we must give a polynomial Rj, which represents the point argument. And furthermore, we also should give Aj and Bj. These specify the left and the right hand side of the path argument, and they are path endpoints. Lastly, we should give homotopy endpoints Qj1 and Qj2. So now you might wonder, what are homotopy endpoints? Well, they are a bit similar to path endpoints, but instead of representing functions, they represent paths in H. The type of homotopy endpoints is inductively generated by quite a lot of constructors. I won't tell all of them, but I will only mention a few. You can use transitivity, reflexivity, the path constructor, the path argument. You can apply the constructor C to a path, and there are much more possibilities. For a precise list of the constructors, I refer you to the paper. Now we understand what signatures are. Next, we look at the Groupoid Quotient, which is the main tool to construct higher inductive types. To understand the Groupoid Quotient, we will first look at quotient types. Given the type X and equivalence relation on X, the quotient constructs a new set X modulo R. Note that we assume that each equivalence relation is propositional, meaning that all inhabitants of R, X, Y are equal. The quotient type is defined to be the following higher inductive type. First of all, we have a constructor CL. This constructor takes an argument of X and it returns the equivalence class in X modulo R. Second, we have a constructor CLEC. This constructor identifies equivalence classes according to R. Lastly, we have a constructor strunc, and this constructor says that the type is a set. The important property of the quotient type is that paths from CLX to CLY is the same as proofs of RXY. The Groupoid quotient is the generalization of the quotient to the one truncated case. That means that the Groupoid quotient does not return a set, but instead it returns a one type. For this reason, we replace equivalence relations by groupoids, because groupoids are a proof-valent version of equivalence relations. Furthermore, the structure of the groupoid, so composition and identities, must coincide with concatenation and identity paths of the Groupoid quotient. The Groupoid quotient is defined as the following higher inductive type. Again, we have a constructor GCL, which takes the equivalence class, and a constructor GCLEC, which identifies the equivalence classes according to the morphisms in G. Now we do not have a constructor that says that the type is a set, but instead we have a constructor that says that the Groupoid quotient is a one type. This is done by the constructor GTrunc. Lastly, we have the constructors GE and GConcat. These relate the Groupoid structure to the identity paths and concatenations of paths in the Groupoid quotient. More precisely, GCLEC of the identity morphism is just the reflexivity path, and GCLEC of a composition is just a concatenation of two GCLX. You can show that equality between GCLX and GCLY is the same as morphisms in G, but there's another important property of the Groupoid quotient, namely that it gives rise to a biadjunction between one types and groupoids. This is just a reformulation of the elimination principle of the Groupoid quotient. Now we have almost everything in place to formulate our main theorem. The only notion that is missing is the notion of one truncated higher inductive type. I won't define that very precisely, but I will indicate how this definition is given. To define one truncated higher inductive types, we first define when a type satisfies the introduction, the elimination, and the computation rules. For the introduction rule, you can just read that off the signature, and for the elimination and computation rules, you need to do a bit more work. Then, with this notion in place, we can formulate our main theorem. Assuming that our type theory supports the Groupoid quotient, then each signature has a one truncated higher inductive type. So now let us look at how this theorem is proven, and for that we'll take several steps. First, we define bicategory of algebras in one types and in groupoids. So an algebra for the signature consists of an interpretation of the point constructor, the path constructor, and the homotopy constructor. So for one types, the point constructor is interpreted as a function from px to x. The path constructor and the homotopy constructor are interpreted as a path and a path between paths respectively. For groupoids, the point constructor is interpreted as a functor, the path constructor is interpreted as a natural transformation, and the homotopy constructor is interpreted as an equality between natural transformations. The second step is initial algebra semantics. So the biinitial algebra is the higher inductive type for the signature. This is proven in the usual way. Next, we construct a biadjunction between the bicategories of algebras in one types and algebras in groupoids. For this, we use the Groupoid quotient. So we already know that the Groupoid quotient gives rise to a biadjunction between one types and groupoids. And what we do here is lift this biadjunction to a biadjunction between algebras in groupoids and in one types. Once this is in place, it suffices to construct a biinitial object in the bicategory of algebras in groupoids. This is because the left biadjoint pseudofunctor goes from algebras in groupoids to algebras in one types. The last step is analogous to how Dipierre and Moncler constructed high-inductive types in the groupoid model. In the remainder, I highlight the following two steps, namely how to construct bicategories of algebras and how to construct a biadjunction. That is because they involve an interesting technique, namely displayed bicategories and displayed biadjunctions. The reason why I use displayed machinery to construct this biadjunction is because constructing this biadjunction directly is rather involved. That is because algebras are rather complicated structures. They have a type, a function, path, homotopies, so they consist of 4 coordinates of data. When we construct parts of this biadjunction, we need to work on all these 4 pieces of data simultaneously, and that makes the definition rather involved. We need to stay in one step how the involved pseudo-functors act on the type, the functions, the paths, and the homotopies. Also, if we construct this biadjunction directly, we cannot reuse the fact that we already have a biadjunction between one types and groupoid. We need to reconstruct it within this definition. The main idea to simplify the construction and to make it more modular is to split it up, and that is what displayed bicategories and displayed biadjunction allow us to do. Displayed bicategories are machinery which allows building bicategories in a modular and stratified way. A displayed bicategory represents structure and properties to be added to an already given bicategory. Each displayed bicategory also gives rise to a total bicategory which represents the structured objects. A displayed bicategory consists of displayed objects, displayed morphisms, and displayed two-cells. The displayed objects represent structures to be added to an object B. Displayed morphisms represent structures to be added to a morphism, and the displayed two-cells represent the structures to be added to a two-cell. Let me give an example of a displayed bicategories over one types. The displayed objects are just functions from ax to x, so this is just the point constructor. And the displayed morphisms and displayed two-cells are just morphisms and two-cells of algebras, so structure-preserving maps and structure-preserving cells. If we have a displayed bicategory, then we can form the total bicategory by pairing. So if we return back to our example, then the object in the total bicategory consists of a one type and a function from px to x. The reason why displayed bicategories are nice is that we can iterate them to form more complicated structures with more intricate dependencies. An example of such complicated structures are the algebras we are interested in. So we define a displayed bicategory over one type, of which the displayed objects represent the point constructor. Second, we take the total bicategory of this one, and on that total bicategory we define another displayed bicategory. Displayed objects here represent the path constructor. Again, we take the total bicategory, and after that we define one more displayed bicategory, of which the objects represent the homotopy constructor. So each piece of data is represented by one displayed bicategory, and they are all untangled. Displayed biadjunctions are a tool to construct biadjunctions between total bicategories. The way we construct the desired biadjunction is by defining 3 displayed biadjunctions. First one for the point constructor, then one for the path constructor, and lastly one for the homotopy constructor. All in all, this allows us to define the desired biadjunction in a more modular way, because we can consider the point constructor, path constructor, and homotopy completely separately. Now let me wrap up the talk. The main message is that one truncated high-inductive types can be constructed using the Groupoid Quotient. All the results in this talk and in the paper are formalized in COG using the Unimod library. Something interesting to note about the construction is the usage of displayed bicategories and displayed biadjunctions. This allowed us to construct the involved bicategories and biadjunctions in a more modular fashion. An important open question is whether we can generalize this construction to non-truncated high-inductive types. Thank you for listening, and I hope to see you during the Q&A session.